Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Pierre Moreau de Maupertuis 1733 Discours sur les différentes figures des astres stands as a pivotal contribution to the Newtonian revolution in cosmology. Central to Maupertuis' work is the question of celestial body shape, specifically the Earth's, and its implications for Newton's law of universal gravitation. Prevailing models struggled to reconcile observational discrepancies with the predictions of Newtonian physics. Maupertuis' Discours directly confronted this challenge, asserting that the Earth's rotation causes its oblateness, a flattening at the poles and a bulging at the equator, a deviation from a perfect sphere. This claim, a direct consequence of applying Newtonian mechanics to a rotating body, sparked intense debate. The Discours detailed Maupertuis' proposed solution and methodology. He championed two approaches: geodesic measurements and astronomical observations. Geodetic measurements, involving meticulous triangulation across vast distances, aimed to determine the Earth's meridian arc length at different latitudes. The difference in arc length, coupled with astronomical north-south positional calculations, provided an estimate of the Earth's polar and equatorial radii, hence its oblateness. Maupertuis meticulously planned and executed an expedition to Lapland to precisely measure a meridian arc. He recognized that a measurement at a high latitude would be more sensitive to the Earth's presumed oblateness. His meticulous recordings and advanced techniques for their time would become a keystone for developing the field of geodesy. The astronomical observations, performed in conjunction with geodetic measurements, aimed to independently verify the Earth's shape. Maupertuis utilized the differing apparent positions of celestial bodies due to the observer's position along a curved meridian. These positional differences, once combined with arc length measurements, yielded a second, independent estimate of the Earth's oblateness. This dual-pronged approach aimed for robust verification, minimizing the influence of any systematic error in one measurement type. The success of this campaign would cement this multi-pronged approach across subsequent works. Maupertuis' work heavily relies on Isaac Newton's Principia Mathematica. Newton's laws of gravitation provided the theoretical foundation for Maupertuis' hypothesis about the Earth's flattened shape. The inverse square law, coupled with the application of Newtonian mechanics to a rotating fluid body, directly predicted equatorial bulging, a prediction that Maupertuis' work sought to verify empirically. The Discours explicitly uses Newton's theory to derive the relationship between a body's rotation and its resulting figure. The text meticulously details the mathematical modelling employed, translating the physical problem into a solvable framework. The derivation involved solving a complex differential equation, a significant undertaking given the limited mathematical tools available at the time. Notably, the Discours itself does not present novel mathematical innovations, rather, it skillfully applies existing techniques to a novel problem. The immediate impact of Maupertuis' expedition and its published findings was substantial. His empirical findings provided strong evidence supporting Newton's theory of gravitation against competing models. The close alignment between observation and prediction significantly bolstered the acceptance of Newtonian physics within the scientific community. While some initial skepticism regarding the accuracy of the Lapland measurements existed, the overall confirmation of theoretical predictions dramatically shifted scientific consensus. The publication of his findings spurred further geodetic surveys globally, refining the understanding of the Earth's shape and, consequently, contributing to a more accurate model of the Earth's gravitational field. The lasting influence of Maupertuis' Discours extends to geodesy and our understanding of planetary formation. The work's methodology, relying on combined geodetic and astronomical measurements, established a paradigm that continues to inform modern geodetic practice. The understanding of planetary figures, directly informed by Maupertuis' work, became foundational in the development of models of planetary formation, particularly in explaining the observed shapes of other planets in our solar system. The Discours did not stand in isolation. Instead, it provided a crucial stepping stone for subsequent rigorous investigations built upon its contributions. The refinement of geodetic techniques and the incorporation of additional observational data over subsequent centuries have only strengthened the fundamental principles outlined in Maupertuis' pioneering work. This essay will proceed by meticulously examining the technical details within the Discours, critically evaluating its methods, and tracing its profound and long-lasting scientific legacy. Detailed analysis of Maupertuis' methodology and results. Pierre Moreau de Maupertuis 1733 Discours sur les différentes figures des astres represents a pivotal moment in the history of geodesy and the confirmation of Newtonian physics. The work's central claim concerned the Earth's oblateness, its equatorial bulge, a direct consequence of its rotation, and Newtonian gravitational theory. Maupertuis' Lapland expedition provided the crucial empirical evidence to support this claim. Resolving a significant scientific debate, Maupertuis' methodology combined geodetic and astronomical measurements. He meticulously measured the length of a degree of meridian arc at a high latitude in Lapland, comparing it to measurements taken at lower latitudes. The theory predicted a longer degree of meridian arc at higher latitudes for an oblate Earth. This difference stemmed from a theoretical prediction of the Earth's shape based on Newtonian physics, a flattened spheroid, rather than a perfect sphere. The core of his calculation involved the relationship between the length of a meridian arc and the Earth's polar and equatorial radii. He did not simply state this relationship instead, he rigorously derived it using known geometrical principles and the principles of Newtonian gravitation. His calculations incorporated detailed considerations of latitude, the curvature of the Earth, and the astronomical observations needed to effectively pin down the precise location on the Earth's surface which he surveyed. Specifically, Maupertuis utilized triangulation techniques to measure the distance between 2 points along the meridian arc. This involved the precise sequence of steps establishing baseline measurements, using angles measured with advanced instruments of his time to calculate the distance between points, and conducting extensive astronomical observation to acquire accurate latitudes. The accuracy of his instruments and techniques are crucial to understanding Maupertuis' success. While imprecise, by today's standards, his methods represented a significant advancement over preceding techniques and represent the cutting edge of the science of his time. The precise mathematical relationship he derived and employed involved trigonometric functions, specifically the calculation of the arc length using the Earth's curvature and measurements of latitude. The astronomical observations were equally paramount. Maupertuis used these observations to accurately determine the latitudes of the points along the meridian arc. These measurements, combined with his geodesic survey, provided the essential data for his calculations. The combination of astronomical and geodetic measurements was integral to his method, offering cross-validation and enhancing the reliability of his results. It wasn't one method, but a synergistic integration of approaches. Maupertuis' results confirmed the Earth's oblateness, providing strong empirical support for Newtonian physics. The measured length of a degree of meridian arc in Lapland was longer than expected for a spherical Earth, aligning perfectly with predictions based on an oblate Earth. He did not merely assert this concordance. Instead, he presented detailed calculations demonstrating the alignment quantitatively. This direct demonstration played a pivotal role in solidifying acceptance of Newtonian gravity, resolving ongoing disputes about the Earth's true shape, and providing a paradigm shift in our understanding of planetary formation. The immediate impact of Maupertuis' work was dramatic. The scientific community widely acknowledged the compelling nature of his findings, shifting attitudes about the Earth's shape and confirming Newtonian gravitational theory. His work became a textbook example of successful empirical validation and directly informed subsequent work in geodesy. The expedition's success established a model for future geodetic research and influenced the methodology used in subsequent measurement campaigns across the globe. His direct contribution laid the groundwork for refined geodetic techniques and extended to our understanding of planetary formations beyond Earth. Subsequent development built directly upon Maupertuis' work. The understanding of the Earth's figure spurred efforts for precise calculation from Newton's theory. These calculations were refined and extended, incorporating more sophisticated mathematical models and observational data. The accuracy of these models, and consequently our understanding of planetary formation and structure, was significantly advanced through his initial finding. While critiques regarding the precision of his measurements emerged, they did not invalidate his central findings or his methodology's fundamental soundness. Instead, these critiques fueled further advances in geodesy and our comprehension of the Earth's gravitational field. Subsequent expeditions and advancements in instrumentation improved the accuracy of the measurements, providing an even more robust confirmation of Maupertuis' central findings. The Discours, therefore, served as a critical foundation for subsequent advancements in geodesy and our understanding of the solar system. Maupertuis' Discours sur les différentes figures des astres, published in 1733, profoundly impacted geodesy and our understanding of planetary systems. His expedition to Lapland to measure a degree of meridian arc near the Arctic Circle aimed to determine the Earth's shape. This endeavour directly addressed a central question within Newtonian physics: whether the Earth was an oblate spheroid, flattened at the poles, as Newton's theory predicted, or a prolate spheroid, elongated at the poles. The Discours detailed Maupertuis' methodology. He meticulously described the triangulation techniques employed in his Lapland expedition, explaining the precise measurements of baselines, angles, and astronomical observations used to calculate the length of a meridian arc. These calculations, based on the principles of spherical trigonometry, directly tested Newtonian gravitational theory. The results, revealing a shorter meridian arc than anticipated at lower latitudes, strongly supported Newton's oblate spheroid model. This outcome held immediate significance. It resolved a long-standing scientific debate, providing empirical evidence for a key theoretical prediction within Newtonian physics. This wasn't merely a confirmation, but a crucial validation of a fundamental aspect of gravitational forces impacting planetary formation. This validation directly influenced subsequent geodesical studies. The method Maupertuis developed, involving precise triangulation and astronomical observations, became a standard for future geodetic surveys. His work spurred numerous expeditions, similar in design, aiming to refine the measurement of meridian arcs across various latitudes. Clairaut subsequently built upon Maupertuis' findings, incorporating advances in calculus to develop a more refined theoretical model of the Earth's figure reflecting the relationship between gravity and the planet's shape. This involved solving complex differential equations to describe the Earth's geoid and irregular surface representing mean sea level. The Discours also advanced our understanding of planetary formation. The confirmation of the Earth's oblate shape provided crucial data to models describing planet formation through the accretion of matter under gravitational influence. The flattened shape implied a centrifugal effect during the Earth's formation, directly resulting from its rotation, an effect that has implications for all similarly rotating celestial bodies. Its direct link between rotational dynamics and planetary shape propelled further research into the formation and evolution of planetary systems. The implications were significant, impacting the study of celestial mechanics and pushing researchers to formulate more nuanced models of planetary dynamics. The earlier models, lacking the precise geodetic measurements provided by Maupertuis, lacked the empirical basis necessary to fully investigate these relationships. The reception to Maupertuis' conclusions was not uniform. Some contemporary scientists challenged the accuracy of his measurements, citing potential errors in triangulation or discrepancies in astronomical observations. However, these critiques did not diminish the overall impact of his work. They instead fueled advancements in instrumentation and survey techniques. Subsequent expeditions employed more precise tools and methodologies designed to address such concerns, providing further confirmation of his fundamental findings. The refinement of measurement techniques continues to this day, constantly increasing the precision of our understanding of the Earth's shape. The Discours exerted a profound influence. Its clear connection to the work of Newton is evident, representing a crucial empirical test of Newtonian gravity. Furthermore, Maupertuis' work directly influenced later researchers, particularly in geodesy and celestial mechanics, including Clairaut's work extending the theoretical foundations of geophysics. His methodology influenced generations of scientists, shaping how scientists approach extremely precise measurements and establishing rigorous standards of data collection and analysis in geophysics. The legacy of the Discours lies not solely in its results, but in its contribution to a rigorous, quantifiable methodology for verifying complex physical phenomena. This methodology contributed significantly to the development of modern scientific practice itself, demonstrating the enduring value of careful experimentation and rigorous data analysis in advancing scientific knowledge. The impact of Maupertuis' work on geodesy and our understanding of planetary shapes and their formation remains substantial, a testament to the enduring power of precise observation and meticulous analysis in the quest for scientific understanding.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.